Welcome to the Probability series presented by Thinking Sphere PH. In this series, we're diving deep into some of the probability topics that most students would find tricky and challenging and are often overlooked. Whether you're tackling these concepts for the first time or just looking to sharpen your skills, you're in the right place. This 10-part series will guide you through everything from the basics of binomial distribution to the nuances of mathematical expectation. Along the way, we'll explore a range of examples, from straightforward problems to those that really make you think. I'll be sharing some helpful tricks, calculator techniques, and shortcuts to make solving these problems easier and more intuitive. So, let's get started with one of the most popular and frequently tested topics in discrete probability distributions, the binomial distribution. Let's dive in. You've probably learned about the binomial distribution using this formula. But what exactly is this for, and when is it applicable? Well, the binomial distribution is a probability distribution used to model the number of successes in a fixed number of independent trials, where each trial has just two possible outcomes, success or failure. Think of it like predicting how many heads you'll get if you flip a coin a certain number of times. Now, for the binomial distribution to apply, there are a few important conditions. First, you need to have a fixed number of trials, like flipping that coin 10 times. Each trial should result in either a success or a failure, with no other options in between. Also, the probability of success needs to be the same for each trial. And finally, each trial must be independent, meaning the outcome of one flip doesn't affect the others. Now, let's break down the formula. The part on the right gives us the probability of that specific sequence of successes and failures. The part on the left tells us how many different ways we can achieve exactly k successes out of n trials. This is called the combination. In the formula, n represents the total number of trials or experiments you're conducting. For example, if you're flipping a coin 10 times, n would be 10. The variable k stands for the number of successes you're interested in. So if you want to know the probability of getting exactly 3 heads, k would be 3. Lastly, p is the probability of success on any given trial. If you're flipping a fair coin, the probability of getting a head is 50%, so p would be 0.5. Together, these variables help determine the probability of getting a specific number of successes in a fixed number of trials. Now, let's dive into some problems to really master this topic. We'll start with a basic example and work our way up to more challenging ones. First up, you roll a fair 6-sided die 8 times. What is the probability of rolling a 3 exactly 2 times? This is a classic example of a binomial distribution because we have a fixed number of trials, which 8 rolls of the die. And each roll is independent, meaning the outcome of one roll doesn't affect the others. Also, there are only 2 possible outcomes for each trial in terms of what we're interested in. Either you roll a 3, which we'll call a success, or you don't, which we'll call a failure. Lastly, the probability of rolling a 3 on any given roll is constant at 1/6, since there's only one 3 in the 6 faces of a dice. Now, let's solve this step by step. The number of trials, n, is 8, because you're rolling the die 8 times. The number of successes, k, is 2, since we're looking for exactly 2 rolls where a 3 appears. The probability of success on any given roll, p, is 1/6 because there's one favorable outcome out of the 6 possible outcomes on the die. Using the binomial formula, the probability of getting exactly 2 3s is equal to the combination of 8 choose 2 multiplied by 1/6 raised to the power of 2 multiplied by 1 minus 1/6 raised to the power of 8 minus 2. So if put these up in our calculator, we get that the probability of rolling a 3 exactly 2 times in 8 rolls of a fair 6-sided die is approximately 0.2605, or about 26.05%. That's it. How about this one? A multiple choice test consists of 15 questions, each with 4 possible answers, only one of which is correct. If a student guesses on every question, what is the probability that they get exactly 5 correct answers? Just like the previous problem, this is another example of a binomial distribution. Here's why. We have a fixed number of trials, which is the 15 questions on the test. Each question is independent, meaning that guessing one question doesn't affect the others. Also, there are only 2 outcomes for each trial. Either the student guesses correctly, which we'll call a success, or they guess incorrectly, which is a failure. The probability of success is constant at 1/4 because there's only one correct answer out of the 4 possible choices. Now, plugging in the numbers, the probability of getting exactly 5 correct answers is equal to the combination of 15, choose 5 multiplied by 1/4 raised to the power of 5 multiplied by 1 minus 1/4 raised to the power of 15 minus 5. And all of these is equal to 0.165, or 16.5%. Let's crank it up and answer this problem. A factory produces light bulbs, and historically 8% of them are defective. If you randomly select 10 light bulbs, what is the probability that at least 3 of them are defective? Now, I know it might seem like a pretty straightforward problem, but you need to be careful here. The key phrase is at least 3. This means we're not just looking for the probability of exactly 3 defective bulbs, we're looking for the probability that 3 or more of the 10 light bulbs are defective. So we could have 3 defective bulbs, 4 defective bulbs, 5 defective bulbs, or even all 10 could be defective, and each of these cases would satisfy what we're looking for. So to solve this, we need to find the probability of getting 3 defectives, or 4 defectives, or 5 defectives, and so on, all the way up to 10 defectives. Now, you probably know by now that when dealing with OR cases, we need to add these probabilities together. This situation is known as the union of events. And as you can see, this could be quite lengthy to solve, especially if we have even larger ranges. So, for this particular case, I'm going to show you a calculator technique to make this process much easier. Here's the trick. Instead of calculating each probability individually and adding them up, we can express this problem as a summation. Just bear with me, and we'll start with the binomial distribution formula. Since the number of successes, k, is varying from 3 up to 10, let's replace k with x and write this as a summation. The equation becomes the summation of the combination of 10 choose x multiplied by the probability of success, 0.08, raised to the power of x multiplied by the probability of failure, 1 minus 0.08, raised to the power of 10 minus x, as x goes from 3 to 10. Now, here's what this equation does. It automatically adds up the probabilities for each of those cases, 3, 4, all the way to 10 defectives. Instead of doing each one by hand, your calculator can compute the entire sum in one step. So, just input this equation into your calculator using the summation function, and you'll get the probability quickly and easily, which actually 0.04 or 4%. This method saves you time and reduces the chance of error, especially when you're dealing with a large number of possible outcomes. Now, what if we change the problem a bit, and this time, we need to find the probability of getting at least 1 defective bulb out of 20 samples. If you use the technique I gave you, you will get an answer of 0.811, or 81.1%. However, this time, I'll demonstrate another method using the concept of complementary probability. Complementary probability is based on the principle that the probability of an event occurring is 1 minus the probability of it not occurring. So instead of calculating the probability of getting at least 1 defective bulb directly, we'll find the probability of the complement event, that is, getting 0 defective bulbs, and then subtract that from 1. Here's how it works. Using the binomial formula, we want to find the probability of getting 0 defective bulbs out of 20. Solving this, we get 0.1887. Then we will subtract this probability from 1, giving us the same answer of 0.811 or 81.1%. How cool was that? When dealing with problems like at least scenarios, using the summation technique is very effective when the range of outcomes is manageable, where the number of trials is not too large and you want to account for multiple specific outcomes. On the other hand, the complementary probability technique is ideal for cases where calculating each outcome directly might be time-consuming. By focusing on the complement of the event, you can simplify the calculation and avoid handling multiple cases individually. This method is especially useful for problems involving at least, where the complementary event is simpler to calculate. Today, we explored how to apply the binomial distribution to various problems, including finding probabilities for specific numbers of outcomes and using complementary probability to handle more complex scenarios. If you enjoyed this deep dive into probability, be sure to check out the other videos in our probability series. Thanks for watching, and good luck on your exam.